Hi everyone, this is part 2 of chapter 7, Gravimetric and Combustion Analysis. Let's get started. In the last video, we discussed precipitation and went over how a crystal grows and discussed nucleation and colloids and so on and so forth. In this video, we're going to start talking about precipitation in the presence of an electrolyte. First things first, what is an electrolyte? You should have heard this in general chemistry. Electrolyte is a compound that will dissociate into ions when it's actually dissolved. Ionic compounds are usually precipitated in the presence of an added electrolyte. Why is that? And we're going to learn about why that is. But a common example that you'll see is silver chloride precipitates in the presence of nitric acid, which is a very common electrolyte, 0.1 molar nitric acid. What I'm showing you here is a colloidal particle. Do you remember what colloids are? Remember, those are particles that are really, really small. They're about 1 to 500 nanometers that pass through most filters. In any event, to understand why ionic compounds usually precipitate in the presence of electrolytes, we have to consider how tiny crystals actually form into larger crystals. A good example of that is the picture that I'm showing you here. Again, it's a colloidal particle, and it's growing in solution that has excess silver ions, proton ions, and nitrate ions. The particle itself has a net positive charge because of all of the adsorbed silver ions. Side note, adsorption means to be attached to the surface versus absorption, which actually means to go beyond the surface. Okay, so I'm talking about silver ions that are adsorbing onto the surface of this particle. So you have this net positive charge because of all these silver ions that are attaching to it, but the region in the solution, right, the region outside the particle is called the ionic atmosphere, and that has a negative charge because, of course, you've got all those silver ions on the outside regions or the border of the particle that's growing, so that's gonna attract all of those negative charges around that. So here's the same picture, just a little bit bigger. It shows you again that the positively charged surface attracts the anions into the ionic atmosphere, but the ionic atmosphere itself is actually negatively charged. And I put there, wait a minute, to become a colloid, you actually have to collide first, right? Yes, you do. Colloidal particles must collide with one another to actually come together, to coalesce. However, these negatively charged ionic atmospheres of these particles repel one another. Because remember, this is just one particle, but you've got a gajillion of these in solution. And all of these have more or less, we assume, the same sort of atmosphere or same sort of stuff going on inside of them, right? So you've got these positively charged, I want to say nuclei, but that's not what it is, right? It's just ions inside, and then the outside boundaries are kind of negatively charged, and you have a lot of these little pockets or a lot of these little colloids coming together. So if you have a lot of these negatively charged ionic atmospheres, they're going to repel one another. So particles are going to have enough kinetic energy to actually overcome this repulsion, this negatively electrostatic repulsion that they have before they can actually come together, before they can coalesce. And one of the things that you can do to increase kinetic energy, very simply, is heating it. Heat the solution up, create some motion in there, and that tends to bring and coalesce things together. Remember the original question? The original question was, precipitates tend to form in the presence of electrolytes. And this is more or less the big finale, right? So if you increase the electrolyte concentration, in this example, it would be nitric acid, that's going to decrease the thickness of the ionic atmosphere. And that actually allows particles to approach closer together before that repulsion becomes significant. So a lot of these gravimetric precipitations are done in the presence of an electrolyte because, again, it helps to decrease the concentration or the thickness of these ionic atmospheres, making it easier for these colloids to actually come together and coalesce. All right, let's move on. The next thing we have to learn is digestion. This is the process of letting the precipitate stand in contact with the mother liquor for some period of time, usually with heating. Obviously, the next question is, what is the mother liquor? Well, that's the solution from which a substance has been crystallized. So this actually might be familiar to biology students if we have any of them in our class, but you basically let your precipitate stay or stand in this solution for a long time, and you heat it really slowly, and that promotes slow recrystallization of the precipitate, which is why we care, right? And at the same time, your particle sizes increase, and you kind of take out all of the impurities from the crystal, so they're expelled from the crystal. So that's why digestion is actually really important, because purity is really important. As a matter of fact, we have a whole section on purity that we have to talk about. So I kind of went over these two words before, adsorbed and absorbed, and we mentioned what they meant. Adsorbed is bound to the surface, and absorbed is within the crystal. But in this section, we're talking about impurities, so we don't want those, right? We want to get rid of those. Now, when we talk about absorbed impurities, so those within the crystal, there's two types of absorbed impurities. There's inclusions and occlusions, or occlusions, I don't know how you pronounce that, but inclusions are impurities that are randomly occupying sites in the lattice, which basically could be occupied by ions that are supposed to be in that crystal. So an example of that is this picture right here on the left. An occlusion is pockets of impurity, and that they're kind of trapped inside the crystal. And as you can see there, possibly they might contain some solvent or something. So obviously they're both bad, but I would think that occlusions is something that's really bad because you've got a huge gap that's growing inside your crystal, which is not supposed to be there. So all three of these impurities, the adsorbed, the inclusions, and occlusions, are said to be co-precipitated. And what that means is just that it's actually precipitated along with the desired product that you're looking for. The book mentions that co-precipitation actually tends to be worse in colloidal precipitates. We know what a colloid is now. So in colloidal precipitates, they tend to be worse. So the whole point here is to try to get your crystals or your precipitates as pure as possible, right? And all the things that we can do to help it would be great. Some procedures actually call for washing away the mother liquor. Remember, the mother liquor is the solution from which the substance was actually crystallized. So washing that away and then redissolving the precipitate and actually precipitating the product. So kind of just doing the whole process over again to kind of get it purer and purer. There's other terms that are discussed in your book, like gathering and masking agent. I would just read over those and be able to decipher between them, but I wouldn't stress too much on those. So the big question is, so how can we get more pure? And in this slide I should have shown before, but you can see right there, it's a way to get more pure is actually redissolving the precipitate and reprecipitating the whole thing again, like I talked about before. And that second time around, you're going to have lower impurities, and your co-precipitation is actually going to be lower as well, which equals more pure. So once you've done all of these steps and you've created your crystal and then you've purified your crystal and you've made sure that they're the right size and everything is beautiful, you got to figure out, okay, what's my final product? And obviously the final product should have a known, stable composition, right? I mean, because if it doesn't, then it's kind of pointless. A term you should be familiar with is hygroscopic, and that's any substance that picks up water. So you have to actually dry it to give a known composition. So anything that it's hygroscopic can pick up moisture from the air, and it's actually really, really hard to weigh it accurately. And that's why, I don't know if most of you remember, but when you took general chemistry, you standardized sodium hydroxide, because sodium hydroxide, when you weigh it on the scale, it's very hygroscopic, so it tends to gain moisture from the air, so you actually have to standardize it to be able to use it for other titrations. So many precipitates actually are hygroscopic and have a variable quantity of water, and thus must be dried under conditions that give a known stoichiometry of water. And hopefully you get zero, right? Zero amounts of water. You get it as dry as possible. Sometimes ignition, or just basically strong heating, right, is used to change the chemical form of some precipitates that don't have constant composition after drying at moderate temperatures. And a very common analysis that we're going to talk about and do problems with is called thermogravimetric analysis. And what they do here is they get the sample, they heat it, and then they measure the mass. And then they get the sample, they heat it, and they measure the mass. So this process keeps on and on and on, and you can kind of see with time, or in this case with temperature, right? With temperature, what is the mass loss of the product? In the picture here, I'm showing you calcium salicylate, and it actually starts out with, it's a hydrate, right? So calcium salicylate plus 1 water, and then they start raising the temperature to about 200 degrees, and you see that it loses that water. And then they start raising it even more to about 300 degrees, and it basically loses half of the molecule. In essence, a benzene ring. But you keep heating it until you actually, the final product that you get is your calcium oxide. So this thermal gravimetric analysis is very simple, it's very straightforward, and it's actually used a lot in laboratories nowadays. Alright guys, this does it for this video. I'm going to resume with part 3 of chapter 7, which will involve actually doing some problems. We haven't done those in quite some time. Alright, see you later.